All right, so question C and D. The thing I want to say about this problem that we could do the problem either way. We can treat it as two blocks that are separated by a thin light string as it is here, and that's fine. Or if you want, we can replace both of those blocks with one block that has a mass of 3m, and it behaves exactly the same. So it's up to you. It's just another set of motion of force equations. If we have the two blocks there, it's one less set if we don't. How would you like me to do it since you asked? Sure. So we're talking about question C and D. It says, consider the initial setup in figure 1. Now suppose that the surface of the incline is rough and that the coefficient of static friction is mu s. Derive an expression for the minimum possible value of m that will keep the blocks from moving, and this is important, down the incline, right there. You got to pay attention to those details because that's what determines the problem. They want to prevent the blocks from going down the incline, which means friction is acting up the incline. That's the detail you had to get from that portion of the problem. There's two ways to ask this question, and in your homework, we asked it both ways. So the minimum value of m to keep it from going down the ramp, or the maximum value of m that would keep it from going up the ramp. Those are the two different ways this problem can be asked. They happen to ask about the minimum value of m to keep it from going down the ramp. So with that in mind, when I look at the forces that are acting on the block on the ramp, I'm going to go ahead and break it up into components. You would probably have to draw a free body diagram on the test in order to get all the points, just like they asked in the first page for you to draw the free body diagram. But I'm going to have them broken up into components already. There's going to be mg sine theta. This is 3mg sine theta down the ramp because we said we're going to treat the block as one 3m block. There is a upward force T2 and an upward force friction. And those are acting along the ramp, or the x direction for the ramp. There's also this component, 3mg cosine theta, and a normal force this way. This is a net force equals 0 problem because we said that the boxes are going to be kept at rest on the ramp. So because of that, the box on the ramp, net force equals 0, and the box that's hanging, net force equals 0. I'm going to choose down the ramp to be positive, which means the block that's hanging up is going to be positive. So that block is only experiencing two forces. It's experiencing T2 upwards and capital Mg downwards. But again, net force is 0. So starting with net force in the x direction for the block on the ramp, I will have 3mg sine theta minus T2 minus friction equals 0. Any question where any of that came from? Alrighty. For the block that's hanging, T2 minus capital Mg also equals 0. And I guess I should point out that the net force in the y direction for the ramp equals 0, and that gives us normal force equals 3mg cosine theta. Any questions there? Alrighty. We are trying to figure out how big this block's mass can be. So we need to find a way to work this together. We could do an immediate substitution, right? Because the net force equals 0, so we know right away that T2 equals mg. So that gives us an immediate substitution that we can do. So 3mg sine theta minus big Mg minus friction equals 0. Now we're trying to solve for m. How big can m be without the system, sliding down the ramp? And my answer has to be an m, mu, and theta. So I obviously can't have f in my answer. So if I solve this for m right now, that wouldn't fly. I need to get rid of that. This probably is going to involve friction, since they already say that there's static friction. So I'm probably talking about having to use friction is less than or equal to mu times the normal force. You know, I'm not trying to hide this, but you probably knew from going in that you're going to have to use this at some point. Seems like now's the right time. And I'm going to substitute into the inequality because I think it's always best to do so. So we're going to take this, solve it for friction, and plug it in on this side. And this is already solved for normal force, so we're going to plug it in on that side. So solving this for friction just involves moving friction to the other side. All right, so I'm going to go off screen here so I can write this. 3 mg sine theta minus big MG has to be less than or equal to mu times 3 mg cosine theta. There, everything's subbed in to my inequality. Any question about that? Do you notice that every term has a g in it? So one of the things we can do right now is just wipe out all the g's. And I want to solve this for capital M. So I'll have 3m sine theta minus 3 mu m cosine theta is less than or equal to big M. So this is kind of what we wanted anyways, but if you read it from the right side to the left side, it says that the mass has to be bigger than or equal to this. So equal to is the smallest it can be, so we have a minimum in place. And so this would tell us the minimum mass necessary to hold the system at rest. Straightforward. This is not one of the challenging questions. I would argue that this one is pretty straightforward, not a particularly complicated, relatively benign inclined plane problem. So I think this, I would be hopeful to see something like this on the test. This is harder if you treat the two blocks separate on the ramp, but not too much harder. You'll find that you'll just have, 2 mg sine theta with a minus T1 and minus friction, and that's going to equal 0. And you're going to have an mg sine theta with a plus T1 minus T2 minus friction equals 0. And those two you add those two together, T1 gets wiped out and you get 3 mg. So it's not really that much more or that many more steps to have treated the two masses separately. So I wouldn't worry about it too much. Treating it as one block is fine as long as they don't ask questions like what is T1. If they ask what T1 is, you're probably going to have to separate it out. And if they have different coefficients of friction, so if block 1 has a coefficient of one thing and block 2 has a different coefficient, then you're going to have to change that. Yeah.
If the blocks were to have different coefficients of friction, would that just mean when you plug the value of n into the friction equation, you would just use whatever value they give you?
Yeah, that's exactly what it would be. So you could be mu1 and mu2 or something like that, or just 0.3 and 0.4, whatever they give you. But yeah. But remember what it would do, though, is it would change the friction on each of these two blocks to reflect the different coefficients.
Okay.
So that would make it would make this question very challenging because the two blocks having different coefficients of static friction would mean that there's actually no way to get the answer directly. Not in a meaningful way, because you'd have two different coefficients, two different values for the frictional force. And that means one of them could hold the block in place and not the other one. Does that make sense?
Yeah.
So, but they're not going to do that. That's their goal is not to see if they can trip you up. Their goal is even in this one, their goal is not to see if they would trip you up. Now, if you want to know how I would modify this question, to be honest with you, I'd modify this question by replacing the string between the two blocks with a spring instead. That's a reasonable modification. That's within our wheelhouse. It would matter in this problem because even in a relaxed state, the spring would be stretched because it's got to hold the two blocks, right? So if it had its relaxed state, you put it on the incline, we know the spring is going to stretch when it gets onto the incline. You'd have the stretch of the spring just at rest with whatever that tension is that's in the cable, and then you could have it accelerate, which would change the amount that it stretches. But I'll remind you that the only thing putting a spring in there does is means that you solve for the tension and then set that equal to k delta x. That's all it is. So it doesn't change the nature of the question in any meaningful way. You just have a tension now that you set equal to Hooke's law. So I don't get worried about the spring questions. And we had a couple in the homework, but nobody asked about them. Yeah.
If you replace something, like in this scenario, if you replace T1 with a spring, can you still treat both of the blocks as one?
For this portion, yeah, you still can. Where the system's, and especially this one, where the system's at rest, right? So nothing's moving. So sure, yeah, even with the spring. Now, the issue with the spring, the real issue, one that we can't talk about yet because we don't have some skills, is that the only time the spring really is something that we can solve is if both blocks have the same acceleration or at rest. But the truth is the blocks probably won't have the same acceleration because the blocks will probably be oscillating. So there's that. And we don't talk about that yet. We will talk about that when we get to vibrations and oscillations second semester. So it's coming back. I wouldn't shy away from it yet. Do you want me to keep going with the one that has the acceleration? Is that next? So the thing about the next part of the problem is that they don't ask for the acceleration. They ask for how fast the block is going when it reaches the ground. So they say the string that's holding the block that's hanging snaps. So all we have left now are the blocks that are on the ramp. Now, you're asked about that a little bit up here. And I don't know what your check boxes are, but I bet you got at least one of the check boxes wrong. Did you do this part? This is where the ball reaches the ground. And the moment it reaches the ground, I would answer question 4 first. The velocity of the blocks on the ramp are still up the ramp. They don't instantaneously stop because the one that was falling stops. So they have a velocity. So they will continue moving until an acceleration brings them to rest, which requires an unbalanced force. Now, there's no T2 right now because the block that hit the ground instantaneously makes T2 go to 0 because there's a normal force supporting that block. We don't need the tension anymore. But these blocks keep going up, but they have an acceleration, down the ramp because mg sine theta is down the ramp. What you probably won't get right is that the tension between the blocks will decrease to 0. And that's because both blocks have the same acceleration, and the only thing accelerating them is gravity. So T1 doesn't do anything to act on either block. So the tension in that would go to 0. This is a very common missed kind of question. But if you even worked it out and tried to solve for T1, you will find that it solves to 0. You can try it, right? The moment you cut T2 and they both have the same acceleration, if you try to solve for T1, you will find that it's 0 because the acceleration of both blocks is just mg sine theta. So now doing this question, you cut the string, the two blocks slide down the ramp, but they have kinetic friction. The thing about this question that I think is hard is that it doesn't ask you for an acceleration or a force or a mass. It asks you for a velocity. So we're about to learn another way to solve this question, conservation of energy. That'll be our next topic, which actually takes solving this question and makes it relatively straightforward. It's not easier than what we're about to do, but all you have at your disposal is to recognize that a force problem can give you the acceleration, and once you have the acceleration, you can use kinematics to figure out a velocity. You would have to come to that conclusion, though. And if you didn't come to that conclusion, that makes this an impossible question. But if you did come to that conclusion, you just need the acceleration. So I don't know who wants to see this one, but do you want me to treat it as one block of mass 3m or 2 blocks? One? Okay. It's probably best because the tension in this case went to 0 the moment the string snapped. So there really is no tension in there. So we have 2 blocks of mass 3m. And we're really only interested in the one block, right? The one that's at the end of the string. It has distance d, but it doesn't matter. We'll treat it the same. The mass, I think you're going to see, is going to cancel out regardless because we're going to get an acceleration. So let's work the problem the same way. I don't want to draw a free body diagram. It's this free body diagram, but without tension. So same thing. And that gives us, down the ramp, 3 mg sine theta minus kinetic friction equals 3ma. Very common for you guys to forget to make the ma part the actual mass of the object, which in this case is 3m. And we're still going to have normal force equals 3mg cosine theta. That's not going to change. But this is kinetic friction, so kinetic friction is equal to mu k times the normal force. So we don't have any inequalities here. We can just do straight substitution. So I'll substitute in for the normal force here, and then I'll substitute that in for friction here. And that gives me 3 mg sine theta minus 3 mu mg cosine theta equals 3 ma. I did skip some steps there. If you need me to fill out the steps, I will. Okay. 3m, 3m, 3m. Right? All the m's cancel out. So our acceleration equals, and if you've done the ramp problems, like actually have done them, with friction, this shows up as the acceleration every single time. This should not be a surprise anymore. I'm not saying that you could memorize this, but it does show up every single time, so you should be looking for it. Right? This is the acceleration of something sliding down a ramp with friction. If it was sliding up the ramp with friction, it'd be a little different because of the directions of the forces would be different. They'd both be in the same direction. Just they're in opposite directions because it's sliding down the ramp. V naught equals 0. Delta x equals d. And we're trying to find the final velocity. So v equals what? I'm going to use v squared minus v naught squared equals 2a delta x. So v equals the square root of 2 times a g sine theta minus mu cosine theta times delta x, which is just d. There, that's it. That's how fast it's going when it reaches the ground. Just pointing it out again, though, if you do this and you add it all up and you get the acceleration and you go back and try and plug the acceleration in to solve for t1, you will find that t1 will equal 0. So that will work. And so you can prove it if you need to, but it's not necessary to prove it. On a smooth surface is attached to a spring that is attached to a fixed point attached to the table. The spring has a known spring constant K. The table is adjusted as shown, making an angle of theta with respect to the horizontal. How far does the spring stretch in terms of m1, k, theta, and fundamental constants? If instead there was a coefficient of static friction between the block and the incline of mu s, there will be a range of possible lengths the spring can stretch. What are they? All right. So let's start by just finding the first one without the friction. So without the friction, eek, I got awful puffy. There you go. I'm going to assume the net force is 0 when it's at equilibrium, and there's no friction, so there's only two forces acting along the ramp. That'll be m1 g sine theta minus the tension in the spring, and so that's going to equal 0. So m1 g sine theta will equal k delta x. So are we looking for delta x here or k? Known spring constant. So delta x equals m1 g sine theta over k. Is that what we're looking for? How far does the spring stretch in terms of that? Yeah, so that's how far the spring stretches. Does this make perfect sense? Let's see. If I increase the angle, sine gets bigger when theta gets bigger, so it will stretch the spring more. That makes sense to me. If I put a heavier mass on there, it will stretch the spring more. That makes sense to me. If I make the spring stronger, that will stretch the spring less. Well, that makes sense. It's in the denominator, so if k gets bigger, the spring doesn't stretch as much. All good? So the next question, if instead there was a coefficient of static friction between the block and the incline of mu s, there will be a range of possible lengths the spring can stretch. This is because if there's static friction, I could pull the spring down a little further and set the block down there, and friction will act down the ramp to try and prevent the spring from pulling it upwards. I could do the reverse. I could push it up a little bit and let go, and friction will be up the ramp to try and prevent the block from going downwards. Does that make sense? So there's two possible directions friction can act in this arrangement. So in scenario number 1, I've pulled the block down further, so I still have mg sine theta, but I also have friction and I still have K delta X here. We'll call this K delta X the longer one, because this is where the spring is going to be longer or elongated. Does that make sense? I'm still going to use the static frictional force, but I'm going to use this. The normal force is still mg cosine theta, so that hasn't changed. So I'm going to have, let's see, mg sine theta minus friction, plus friction minus k delta x L equals 0. So friction equals k delta x L minus mg sine theta. And I'm going to plug that in for my frictional force. So k delta xl minus mg sine theta is less than or equal to mu mg cosine theta. So solving for delta xl, I'll get delta xl is less than or equal to, and then we get all this garbage, mg sine theta minus mu mg cosine theta, all divided by k, which isn't negative, so this will be the greatest delta x can be. And we're right there. Delta x can be less than or equal to this, which means this is the biggest it can get, right? It can be smaller than this, but it can't get bigger than this. Yeah?
Would it be plus? The mg sine theta plus?
Yes, I'm sorry, this would be plus. Yeah, sorry. Now, the other side of this is to move friction over here, right? That's going to make the frictional force here negative, right? That's how this problem changes. And this is no longer XL, this is XS, for as short as it can be. We still need to solve this for friction and sub it in. So I'll solve this for friction, and I'll get mg sine theta minus k delta xs. Okay? Good to keep going? All right. So let's see, mg sine theta minus k delta xs is less than or equal to mu mg cosine theta. Let's see, I want to solve this for xs, so mg sine theta, sorry, it's getting a little sloppy, mu mg cosine theta has to be less than or equal to k delta xs, and so divide by k, and we'll get delta xs has got to be greater than or equal to mg sine theta minus mu mg cosine theta all over k. Yay. Again, this is, the top of this is a smaller number because we're subtracting. We expect it to be smaller, and it is smaller. Also, it's a less than, or sorry, it's a greater than or equal to. So I can have the spring bigger than this, but it won't be any smaller than this. If it gets any smaller than this, then friction isn't enough to hold it in place, and it goes down. Yay. Now, would you have both of these in the same FRQ? Probably not. If you want to talk about the test a little bit, and I think that that's a reasonable thing to do.